In section 6.3, we are learning about the second fundamental theorem of calculus. The first fundamental theorem told us about the relationship between definite and indefinite integrals. The second one relates a derivative and an accumulation function. So we already have this idea from 6.1 that the derivative and the antiderivative are inverse operations. So if I take the derivative, so remember d dx tells me I'm going to take the derivative with respect to x of this indefinite integral, or I could think of this as an antiderivative. Well, these things are going to undo each other. So if I find the function that is the antiderivative of 3x plus 2, we know that that function would be 3 halves x squared plus 2x plus c, some constant of integration. And following the order of operations, we would think of all of this as like being grouped together. So we're doing our grouping. So once we find that antiderivative, we then apply the derivative, so d dx, and unsurprisingly, we are back where we started at 3x plus 2. So we took the antiderivative of 3x plus 2, took the derivative of that, and we could see that the derivative and the antiderivative undo each other. So generally speaking, taking the derivative of an indefinite integral or of an antiderivative, there's this process of undoing, and we're back with the thing we started with. So before we move on to applying the second fundamental theorem to accumulation functions, I just want to remind you again, like what an accumulation function is and when we might use it. So I have this problem that I pulled from a homework question from 5.3.2, and I actually wrote a different question underneath. So one of the things you did on this practice is you were given this function t of t, where uppercase T is the rate at which temperature is fluctuating or changing. It's very annoying to me that uppercase T is not temperature, but it's the rate of change of temperature. So T is measured in degrees Celsius per hour, lowercase t for time is measured in hours, and we're given the temperature at 0 is 23 degrees Celsius. So we have to name some other function if we're going to write an accumulation function. So we do not currently have a function that represents just the temperature, so we might have to name that, and I'm just going to call it C of t, where C at least maybe aligns with degrees Celsius. I know that's kind of backwards. So let's let C be the function that represents the temperature in degrees Celsius at any time t, such that the derivative of C, the rate of change, is the function t that we were given. So this is a graph of t, which is C prime. So recall that when we integrate t, or C prime, so in this case, these would be the same thing since we said C prime is t. When we integrate, this is going to tell us about the change in temperature when we integrate the rate at which temperature is changing over a closed interval. So what this tells us, either way, the shaded triangle under the x-axis, or if we write it out as this definite integral, this tells us that between the time 0 and 4 hours, t equals 4 hours, the temperature changed, or we could even say decreased, since it's negative, by 6 degrees Celsius. So that's what we learn, and that was part of a question that you answered on your homework. So one of the homework questions that you were asked is, what is the temperature at t equals 4? Like, what is the temperature at t equals 4? Well, in order to find that out, we have to know some value of the temperature at some other point in time. And sometimes we might think of this as an initial condition, kind of like what we talked about with finding our constant of integration with the antiderivative. And don't let the word initial fool you. It's not always at 0. But in this case, we're given the temperature at 0. So according to the function that I wrote, I could think of C of 0 is 23 degrees Celsius. And if I want to know the temperature at T equals 4, what I'm trying to figure out is what is C of 4? Well, that's going to be whatever the temperature was at 0 plus the change from 0 to 4 of, we would integrate the rate of change of the temperature. So C prime, or in this case, T of T, since that's what the function was named. The way this function's named is driving me crazy, but that's its name, and I didn't get to pick it. Okay, so this tells us C of 4. This tells us that we're starting at 23 degrees. That's what our C of 0 is, 23 degrees Celsius. We're adding to that the change of the temperature between 0 and 4 hours, which we know from over here is -6. And so we would figure out that C of 4 is 23 minus 6. So what's that, like 17 degrees Celsius? I'm not actually really worried about the answer. What I'm worried about is the second question. So if we wanted to write a function so that we could find the temperature of any time t, like if I want to be able to find the temperature when t is like 1.7, we could do that, and that's an accumulation function. So it's based on what we wrote. It's based on this equation, except I'm going to replace the 4 with t. My starting value would still be the thing I know, so C of 0. And then the accumulation part happens here, that we're going to add the change in temperature from 0 to whatever this time t is. And remember that when we do this, we said that the t's in our integrand, we have to replace those with a dummy variable, which I hope to explain during this lesson. But I'm going to just replace those with x. It doesn't matter what the variable is. It just cannot be t. So this is what we call an accumulation function. And another accumulation function related to this one is if I just wanted to know the change in temperature from 0 to any time t, I could drop my 23 degrees, my C of 0, and I could write a different function for that. But I'm going to leave this one. So I wanted to refresh your memory on what an accumulation function is, why we might write one, why we might use it, and let's go back to the second fundamental theorem. So I'm going to skip down to this middle text, and we already said that the derivative and the antiderivative undo each other. So let's look at what happens when we take the derivative of an accumulation function. So in this example of g, we're going to interpret a as a constant number, the lower bound or the lower limit of integration, and x is going to be the true variable of integration. So I can also tell that because the function is g of x. So these t's that we're left with, f of t, d of t, again, that's what we call a dummy variable. So when we apply the fundamental theorem, it will be replaced with x. So I know that this example is written out, but I'm going to kind of walk us through it because it's a lot to look at. So first, we have similar to the example we started with, except this is now written as an accumulation function. The way I know is that I have a variable as one of my limits of integration. So I can see that I've got this function 3t plus 2, and I'm going to integrate it. My variable of integration is x, but then I'm going to take the derivative. And this looks like a lot of work, but hopefully the result won't be surprising. So instead of writing this all out, let's just kind of follow through. All right, so the first step is if we have this 3t plus 2, we could find the antiderivative. Normally, like in the example above, we said we would add a constant of integration. However, since this is not an indefinite integral, but it has limits of integration to and x, that's unnecessary. Because if we look at what happens, next step, when we evaluate the antiderivative for the upper limit minus the lower limit, all of this that I am underlining in coral or whatever color that is the antiderivative evaluated at this upper limit x. And then remember that first theorem tells us that we're going to subtract the antiderivative evaluated at the lower limit 2. And when we do that, we get 3/2 x squared plus 2x minus 10. All of this stuff is 10. So then, so if we'd had a constant of integration, it would have just gotten subtracted out. But now we're ready to take the derivative of that. And when we take the derivative, well, that 10 is a constant, so we're left with 3x plus 2. So you might be asking yourself right now, oh my goodness, do we have to do all of that work? And the answer is no, absolutely not. That's what the second fundamental theorem of calculus gives us, is not having to do all of that work. What we can do instead is realize that when we take the derivative of an accumulation function, like that's what we're doing in this process, that if we just have the variable x as our upper limit of integration, that essentially this just all becomes 3x plus 2. So the derivative and the integral undo each other, and that dummy variable gets replaced with x. So more generally, if I have f of t and I'm integrating that from some constant a to a true variable of integration x, and then I take the derivative of that, in the order of operations, we do all that stuff before taking the derivative. Well, we could skip all the work in between. That's just going to give us f of x, not f of t. So the second fundamental theorem, and it's hard to I remember learning about this when I was a student. It's hard to understand at first, like why this is important or why we would need to do it. Of course, we'll build that understanding in. But this is it. This is our second fundamental theorem, that the derivative of the definite integral is essentially the function with the variable of integration, not the dummy variable. Now we're going to see an example at some point of when it's not quite that simple. And that's going to come on the next page. So let's look at these simple ones. In this first example, don't think we have to do a complicated antiderivative. We don't. We see that we've got a function. We know that there's a dummy variable t because I see that this is an x. And so the derivative in the indefinite integral or the antiderivative, those are like inverse operations. We're left with x ln of x minus 5. So we get back the function in terms of our variable x. All right, the second example, well, the same thing. I bet you could guess it. We're going to be left with 3 times the sine. Instead of x, my variable of integration is t minus the cosine of t squared. All right, the last one though, watch out. This one could be tricky because look at where the x is. The x is on bottom. The x is our lower limit. And in the theorem, the x must be the upper limit. So what we could do first is we could do a reversal of limits. So remember that the reversal of limits would cause us to multiply by a -1. So we would have -1 times my integral. Now 0 is on bottom, x is on top, and then I've got 4e 3 to the 3t squared dt. And that -1, like, we can leave it on the outside. We could put it on the way outside of the derivative, or using kind of the inverted constant multiple rule, we could put it on the inside. So this is the same as taking the derivative of the definite integral from 0 to x of -4e to the 3t squared dt. So now we can just apply our theorem, and we're left with -4e to the 3x squared. Okay, so the next example, we're given the accumulation function g of x, and then we're given some more stuff. We're given f of x, and we're asked to evaluate, I'm so sorry, I'm so tired. We're asked to evaluate g of -1, g prime of -1, and the second derivative of g also at -1. So my advice is to write it out. It's not that bad if we write it out and we just substitute the -1 as needed. So when I find g of -1, I'm just replacing x with -1. So I'm going to basically copy this function. And so now I have from 0 to -1 of f of t dt. And actually, as I'm writing the t's, I'm going to replace that with x. The only reason that placeholder t is there was because we had an x. But now that I'm filling this in, I'm going to say f of x dx. Okay, so this is not that second fundamental theorem. In this case, we actually need to find that antiderivative. So g of -1 is the definite integral from 0 to -1 of, and I'm going to now write in my 3x squared plus 5. Okay, so as we find our antiderivative, we know that we're going to have x cubed, so 1/3 3x cubed, plus 5x. And since we have limits of integration, we don't need a plus c, but we're going to evaluate this from 0 to -1. So that becomes -1 cubed plus 5 times -1. So -1 minus 5, and then we're going to subtract from that the lower limit. So 0 cubed plus 5 times 0. So -1 plus -5 is -6 minus nothing. All right, so g of -1 is -6. All right, so that one we just got by plugging -1 in. The next one, when we go to find g prime, remember, to find g prime of -1, we have to know g prime of x first. So this is where that second fundamental theorem comes in. When I take the derivative, I'm taking the derivative of an accumulation function. Like g prime of x is the derivative of this function. So we get f of x. It's that easy. So g prime of x, in this case we could say, is 3x squared plus 5. Therefore, g prime of -1 is 3 times -1 squared plus 5. So that is what? 3 plus 5, 8. All right, lastly, to get the second derivative of g at -1, well, we already have an expression for the first derivative of g. So just taking that, I can get my expression for the second derivative. Just take the derivative of 3x squared plus 5, so 6x. So the second derivative of g evaluated at -1 is -6. So of course there's a more complicated possibility, and that is when we have to use the chain rule. But don't panic, it's not that bad. This is the same chain rule from when we take a derivative. So when this happens, or when we have this more complicated thing happen, it's when our limit of integration in our accumulation function is not merely an x. It's a function of x. So for example, in these next two examples, I could see it could be an x squared, or it could be something like 5 times x. And let's just look at what happens when we go through the steps. We find the antiderivative and then take the derivative. So if our function is lowercase f, and we're integrating that from a to some function of x that we're going to call g of x. Well, our antiderivative is uppercase f, and we're going to evaluate that from g of x, or well, from a to g of x. So we're going to do uppercase f of g of x minus f of a. And that's all the first fundamental theorem from section 6.2. So we find the antiderivative and input the upper lower limits and subtract in that order. And so then we're going to take the derivative of both of those. But remember, a is a number. So f of a is a constant. So the derivative of f of a is going to be 0. So what we really just have is the derivative of f of g of x, uppercase f of g of x. And so if you recall, that is literally the chain rule. That is, like, by definition, the chain rule. So we're going to take the derivative of the thing on the outside, which is uppercase f. And remember, the derivative of uppercase f is lowercase f. We're going to keep the junk on the inside, but then we're going to multiply by the junk on the inside. Okay, so all this to say, when we use the second fundamental theorem and we have a function of x instead of plain old x, we just got to multiply what we get by the derivative of that function of x. And it's because of the chain rule. And it looks so much worse than it actually is. So let's apply it in these next two examples together. So if we are, I wish these were numbered. I'm going to call this example 1. If we look at this first new example where we're applying the chain rule, well, we know that because it's an accumulation function, that we're going to replace the sign of t with this limit of integration. So it's not just x, but it's the entire function. So we get the sine of x squared. But then we have to multiply by the derivative of x squared using the chain rule, which is 2x. So our final answer, I would just put the 2x in front. So 2x times the sine of x squared. All right, for that second one, how about this? What I'd like you to do is I want you to pause the video. I want you to try that example and then try the one beneath it and then unpause the video and we'll go over it. All right, hopefully you gave yourself some time to try those examples. The second chain rule one up here is a little trickier. So anywhere we see a t, we're going to replace it with 5x. Be careful that we do that in parentheses. We always substitute into parentheses. So that becomes 5x times 5x, not like just 5x squared. And over here, we're going to have, instead of t e to the t, 5x e to the 5x. But don't forget the chain rule. We got to multiply all that by 5. So our final answer should be 125x squared plus 25x e to the 5x. All right, this last example, we'll just call it number 3. This is a good one. I love this problem. All right, so for part A, when we evaluate g of 2, just plug 2 into the function g up here. And what we're really doing is finding the area between x equals 1 and x equals 2 bound by f and the x-axis. So that should be -1/2 since we're moving left to right and it is below the axis. To find g prime of 2, we got to find g prime of x first, and that is the second fundamental theorem. So g prime of x is just f of x. So g prime of 2 is just f of 2. And on the graph, we could see f of 2 right there, -1. Lastly, we're asked to find the second derivative of g at +2. So that's going to be the first derivative of f. So if g prime is f, g double prime is f prime. So f prime of 2 is -1. And how do we know that? Well, we have to find the slope of this line. So if I pick like 2 good points, I'm going down 1, over 1. My slope is -1/1. Part B. These get pretty tough. You really got to think about these. Determine the intervals on which g is concave up. So if I just back up from unit 4, I know that if g is concave up, that means that g prime is increasing. And that also means that my second derivative is positive. So we still have to relate these facts back to f. So where g double prime is positive, that means f prime is positive. And that's also going to be where f is increasing, or g prime is increasing. So if I look at my graph, that's from -1 to 0, then we're decreasing some more, and then from 3 to 5. In part C, determine the location of all relative minima of g. So we could examine all of the critical values, but remember, like if I have a sign chart and if I want to find minima of g, I'm looking for where the derivative g prime is changing signs. So I'm looking for values where g prime goes from negative to positive. That's going to tell me that g is going from decreasing to increasing, and I can see that that would be the location of a relative minima. So I'm looking for where g prime changes from negative to positive. And again, my graph is of f, but we established in part A that g prime and f are the same thing. So if I want to know where g prime changes from negative to positive, I'm really looking for where f changes from negative to positive. And that only happens once at 4. So there is a relative minimum of g at x equals 4, because that's where g prime, or f, changes from negative to positive. All right, lastly, part D, and I didn't write out the answer all the way yet. Find the average rate of change of g prime on the closed interval 3 to 6. So again, we said the fundamental theorem tells us g prime is f. So f of 6 minus f of 3 over 3, we get 2/3. Must there be a c on the closed interval 3 to 6 such that, or where g double prime of c is 2/3? So if we've established that the average rate of change of g prime is 2/3, and we're asked about the derivative of g prime, this is hinting at an MVT problem. So let's remember the hypothesis of the MVT. If we're using it on the function g prime, the hypothesis would tell us that g prime must be continuous on the closed interval 3 to 6 and must be differentiable on the open interval from 3 to 6. And also from part A, we said g prime is f. So when we look at the graph, we're looking to see, is f continuous on the closed interval 3 to 6, differentiable on the open? So I'm going to erase all this junk that I wrote on here already. It's a nice thing about doing this in OneNote. All right, so if I look at f from 3 to 6, I could see that f is continuous. However, is f differentiable? No. At x equals 5, f has a corner. And so the slope from the left does not match the slope from the right, or the derivative from the left does not match the derivative from the right. So I cannot apply MVT. So we cannot guarantee this with MVT. And furthermore, if you just look at the graph, like if G prime is F, this is really asking us, must F prime be positive 2/3? Well, let's just look on the graph. Is it ever 2/3? So from this point to this point, my slope is positive 2. And then my slope becomes drastically negative 2, in fact. So I can actually see that not only can MVT not guarantee that value 2/3, but the graph can prove that there is no value of x where the rate of change of f, the instantaneous rate of change, would be positive 2/3 on that interval. I know that's a lot to think about, and these questions get a little bit meta when we're, using f to describe g, but that's what makes it so fun. All right, that's what we've got in section 6.3.